Let's introduce my proposal. So according to COVID-19 in 2020, our school needs to deliver a class via Zoom, but it's very hard to meet the requirements since every student have to take the online courses. So the demand is too much, and the school can't sit just one website to deliver the Zoom lecture. So our school decided to set three websites according to the school department: the engineering, McKelvey Engineering School, Audience School, and the medicine school. So this three websites can deliver lecture to two locations, the US and China. Basically, most students are come from these two regions, and it's very hard for the website to directly send the videos to these two regions. It can directly send, but the number is limited. So the school have to rent the satellite to send the video to satellite, and satellite as the transfer state to transfer the videos to these two regions. So here's I define GOM, which means James McKelvey School, Audience School, Medicine School, and the requirement for each department is like 200 for our engineering school to send videos per year. And these two regions are the demanding nodes, and the demanding videos is here 400 and 200. And this table shows the cost from place to place. Like from our engineering school to the US, it will cost $0, but when it's sent to a satellite, it will cost $1 per videos. And basically the same for the audience, the med, and the satellite to the China, satellite to the US. And here's the table for the capacity, which means like for our engineering school, it can maximally send 50 videos to US, and it can send a lot of videos, like 175 videos to the satellite, and satellite can transfer. Like satellite can transfer videos to the US, and the capacity is 200 and 150 to China, which is quite large. So I fit these three tables into the graph, and here is the capacity demand graph seen here. So 50, all the green numbers are the capacity for each arc, and the black number are the requirement, like the requirement for each department. So for our engineering school, it requires to send about 200 videos, and for audience is required to send 300, etc., etc. And this is a cost graph, which means, for example, from our engineering school to the US, it will cost $0, as I mentioned before. And for our engineering school to the satellite, it will cost $1 per video. And combine these two figures, I will construct this final plot. So basically, the blue number means capacity for each node and arc, and the black number are the cost for each arc. So after this, I will transfer my proposal into the minimum cost flow problem. So here, basically, the objective function is based on the cost relationship. For example, from J to U will cost $0, so here's a 0, and from G to S1 is cost $1, so here is the XG S1. So plug all this arc together, I will construct this objective cost function. And for the constraints, so it's based on each nodes. For example, here this node it requires 200 to send out videos. So XGU plus XGS1 equals to 200, and etc. etc. Here's the basic format for the minimum cost flow problem. And after this, I will propose one solution. I propose like the basic arc is G2S, O2S1, and basically all the lines here, the true lines here are the basic arc, and for the non-basic are the dashed lines here. So I propose, and we have to travel to circles to find that whether the arc is the optimal or not. So after travel through these two circles, I find that like for CS2, it's not the optimized solutions. So I have to decide. I have to do more iterations to find the best, the final arc, like final solution for this network. So as a requirement, I use this package SCIPY to do the minimization. And here I define the objective function here, and 7 constraints here. The returns are the constraints here. So 7 constraints. After this, I will set all the constraints to the equal constraints and do the bounds, which represents capacity for each node. And after this, I will set the initial value equal to all the 50s. This is a random value. I can set whatever I like. So and I use SQP solver because it can solve the bounds and the constraint at the same time. So after this, this solver can finally give us the results of this is the final result, like the minimum cost for the school for the school to deliver the online courses by meeting the requirements, meeting the students' requirements. And basically, these are the arcs. Each arc's capacity, each arcs are sending this kind of videos. We will plug this into each arc, and finally, this is the final result. Like our school have to pay like $1,168 to meet the requirements. And here is the final flow for this problem. So next, I will do the sensitivity analysis. I will set these models as before, same as before, to this clips as taught in class. This and to do the optimization and the sensitivity analysis. And after this, here are the results. So to do the sensitivity analysis for objective function, and this is a constraint. So for the objective function, here's all the sensitivity variables here. So when we focus on the current, the X10 is very important. So when we do like we have to focus on the X10 when we change its cost, the parameters in front of X10. And here are all the range for each parameters. And also here is all the range for the constraints. And when we want to change the parameters, we can check whether which parameters is important. And for the inaccuracy analyze, like if accidentally there are some inaccuracy observed before. So for this, like X1 and X6, this two, if there is some inaccuracy observed here, it still will not affect the final result. But if there is some accuracy, like 10% from X10, it will affect the final result. And here's all I want to say. And thank you.